Welcome to the ChemDoctor, and this video is being produced in response to a request that I've had on my website to produce more videos that help the viewers with theoretical yield and limiting reactant. All right, so let's go ahead and get started. So we have a chemical reaction between hydrochloric acid and oxygen to produce water and chlorine. And you can see that we've been given mole amounts of both of the reactants. The mole amounts that we've been given are in the same units as the coefficients of the balanced equation, and that's a really important first step to this, is to look and see in what form of the amounts have you been given, because if we were given mass, for example, the first thing we would have to do is get both reactants in the form of moles, because moles are the units of the coefficients, and I want to emphasize that here. So the coefficients are in units of moles. So one of the important aspects of these problems is to always make sure before you start down the calculation road to determine what unit that you've been given in terms of the amounts. And we've been given mole amounts of both reactants. So we actually can start in terms of our calculations to determining mole ratios to calculate the moles or the theoretical yield of a designated product. So that's the next issue here. We have to know which product we're being directed to find. And in this case, what we're going to do is calculate the theoretical yield of the water. All right, so theoretical yield, and in particular, we're going to find the theoretical yield of water in mass units. So we're going to have to solve for grams in terms of the theoretical yield. All right, now we have established which product that we're looking for, and what we need to do now is figure out which of these two things is limiting. Remember, the limiting reactant is the reactant that, based on the ratio in which the reactants react, is going to run out first. And once that reactant runs out, then the reaction is going to stop. And once the reaction has stopped, that reaction has produced the maximum yield, the maximum amount of a particular product that is possible. All right, so the way to handle this, and again, we're in moles, and I think that some of the viewers are going to be able to look at this right now and just compare to the ratio from the balanced equation and tell which of these two reactants is the limiting reactant. But in most cases, if you're like me, you want to use something mathematical in order to unambiguously calculate a number that you can use to determine that issue, so that you can't get confused or turn something around. So the way to do this is we're going to calculate the theoretical yield of product of water produced using both reactants in independent calculations, pretending that the other reactant is in excess. So what I'm going to do is drop down the information that I've been given for both reactants in what I call a stack. So I have my 6 moles of HCl, and then right underneath it I have my 3 moles of oxygen. And what we're going to do is calculate the theoretical yield of the water. And since we're already in the same units as the coefficients, what we're going to do now is utilize a ratio from the balanced equation to solve for the H2O. So we're going to pull down the coefficient for the H2O, which is 2, put the label in that indicates what we're solving for, and that information needs to be in the top of the fraction for both calculations, because we're solving for the amount of H2O produced using both reactants as if the other reactant was in excess. So we need the 2 from the balanced equation in this position in both cases. Now, in the top reaction, we want the moles of hydrochloric acid to cancel out. So in the denominator of the fraction, for the top calculation, we're going to need the 4, the coefficient from the balanced equation here. And for the oxygen, we're going to need the 1. All right, and now we go ahead and we calculate for both of these the moles of H2O produced. And remember, what we're going to do is get our values here, and we're going to compare the two of them to see which is the smaller number. And whichever has a smaller theoretical yield, that had to come from the limiting reactant. Now, for the top reaction we see here, or the top calculation, this is going to be 1 over 2. So 6 divided by 2 is 3. So for the top calculation, the maximum theoretical yield is going to be 3 moles of H2O. For the bottom one, we have 2 times 3, or a maximum of 6 moles of H2O. All right, so now, comparing these two numbers, you can see that the top calculation produced a smaller amount of water than the bottom one did. So I'm going to come back over here and I'm going to circle the hydrochloric acid. This is my limiting reactant. So I'm going to abbreviate this LR. I'm going to label it as limiting reactant, the LR. And the oxygen, therefore, is the thing that is in excess. Now, like I said at the beginning of the video, we're going to solve for the water in grams. So now I just need to come back to my top calculation, and we're going to multiply the 3 moles of H2O by the molar mass of H2O. Now, to find molar mass, all right, we need the molar mass of H2O. There are 2 hydrogens, and each hydrogen's worth 1.008 grams per mole. Look this up on your periodic table. Plus oxygen, which is 16. So the grand total is going to be, we're just going to round this, it's going to be 18 grams per mole for the molar mass of the H2O. So that's what we now need to place here. And we see the maximum mass that we can get from this is going to be 54 grams of H2O. This is our theoretical yield, which is the maximum mass of water we can produce in this reaction if it goes to 100%, uses all 6 moles of the HCl, and there are no losses. Now, in this video, we're going to extend the sophistication of what it is we're doing, and we're going to calculate the mass of the remaining reactant. So we're going to calculate mass of the excess, mass of the oxygen left over after the reaction is over. All right, now this is going to take, whoops, I need an R here, sorry about that. Now, this is going to take 2 steps. In step number 1, we're going to calculate the mass O2 used in the reaction. And then step number 2 will be to use that value to determine, all right, the amount, and I'm going to abbreviate amount as AMT, of O2 that remains. So this takes 2 steps. Now, step number 1, what you need to realize is that once we know the limiting reactant of the problem, we have to use this value to solve for everything else. You can't use the excess to do this. So I'm going to circle the moles of H2O maximum that was produced in the reaction, and then I've already circled the 6 moles of the HCl, which is the limiting reactant. You need to realize that you could use either of these values to solve for the oxygen to figure out how much oxygen it was used. Now, to be consistent with what I normally do in my classroom, I'm going to stick to strictly using the moles of the limiting reactant. So we're going to pull this down, and I'm going to rewrite it. I've got 6 mole of HCl. And what we're going to do first is, since again we're already in moles based on the chemical, the coefficients from the chemical reaction, so we're ready for the ratio from the balanced equation. So I'm going to multiply this times fraction bar, and we're solving. I'm going to write it down over here right now so I know what it is I'm solving for. Mole of O2 used up in reaction with the HCl. Let me just fix that a little bit. With the HCl. All right, now what's that ratio going to look like? All right, in the numerator we're solving for the O2, so I need the coefficient again. For the O2 it's 1. And I want to cancel the HCl, so we're going to have 4 HCl's down here. Maybe I'll change the color of the 4 so it's really standing out. All right. Now you can see moles of HCl cancels with the HCl, and we have 6 divided by 4, so the maximum O2 used in the reaction is going to be 1.5 mole of O2 used up in the reaction. Now you can see that we were given 3 moles of O2 to start with. So I'm going to bring that value down over here. We have 3 mole of O2. This was our excess, so I'll label it excess. It was given to us in the reaction. And we're going to subtract from that the amount that was used. So we have 1.5 moles of O2 that was used up in the reaction. Used up. Here's the excess. And here's the stuff that was used. So that means that after the reaction's over, we're going to have 1.5 mole of O2 that is unreacted. This is left over after the reaction. Now, if I want the mass of this, I can multiply times the molar mass of O2, all right, and the molar mass of O2 is going to be 2 times 16 grams per mole, or 32 grams per mole. So this is going to be times 32 grams of O2 per mole, or after the reaction's over, we're going to have 48 grams of O2 that remains. All right. Now, with that, I'd like to go ahead and close the video. I'd like to thank the viewer for watching. You can find more videos at www.chemdoctor.org. Thanks again for taking the time to watch my video, and hope to see you again.